carbonaceous contrast.
Quick, I guess you're all quite tired. So what I want to talk about is carbonaceous contrasts, and first I want to tell you why they're exciting and why I'm fascinated about them and what they can tell us about astrobiology. So just a sort of very short overview of meteorites in case you've never encountered the expression carbonaceous contrasts. Meteorites come in very many different shapes, but they can be categorized in three different categories as stony meteorites, as stony iron meteorites, and then you have the metal there, and then there's pure iron meteorites, and that tells you something about the origin. And then when they descend through the Earth's atmosphere, they get a fusion crust, which is this black thing. So that means that when they're not so big that they actually end up evaporating and making an impact crater, but they're sort of smaller, so they survive going through the atmosphere. Then what happens is that the outer layer is melted off, but at the same time the wind cools down the meteorite, and since the meteorite is not stone is not a very good heat conductor, then the interior of the meteorite is actually intact, so it doesn't get heated off. So you just you peel off the outer layer, and the fusion crust is only a few millimeters thick, and the interior of the meteorite is left untouched, as it was originally when the stone was in space. So there's eyewitness telling that they saw a fireball coming down, they saw the meteorite land, it broke into two, and then it had frost on the inner surfaces simply because it had the same temperature as the outer space, although it was hot on the outside. The most common type of meteorite found is the chondrites, and they make up about 86% of all the falls which have been seen. That means if you go to a museum, they don't make up 86% of the collection that you see, because what you mainly see in the museums are iron meteorites. And that has to do with the fact that it's much easier to recognize an iron meteorite if you find it in a garden, because you find this big chunk of iron, you think, what is this? You send it to your geological museum. If you find a stone like this, I mean, how would you know that it's not just whatever, right? You would just throw it off and think, where did it come from? The chondrites, they come in different families. There is a group called enstatites, there's a group called ordinary chondrites, and there's the carbonaceous chondrites. And it seems like the enstatite probably formed in the inner solar system, the ordinary chondrites probably are from the asteroid belt, while the carbonaceous chondrites, which are the least altered and most primitive, probably comes from either the very outer edge of the asteroid belt or maybe even further out. There's some people who claim that maybe carbonaceous chondrites are actually sort of dried out cometary cores. The reason that they're called chondrites is because they contain chondrules. And I have this little piece of a ordinary carbonaceous chondrite which I'll send around, and there you can see the chondrules. And chondrules are these little round inclusions which are from sort of nanometer to millimeter size. And if you have a piece of ordinary chondrite in your hand, you can always say, oh, I have a whole bunch of planets here, because this is believed to be the first thing that condensed out in the solar nebula. Then you had these little droplets condensing out, and they later went together and became the planets. So one could say that these are actually sort of the first very early planetesimals. Exactly how they formed is still a big mystery, because what can be seen is that you have these chondrules which have been heated. So I mean they were done in a very fast heating event, and then they cooled very quickly. But exactly where the heat came from is a big question. So there's different stories about it could have been during the formation of the solar system, that there was some sort of flare from the sun, could have been a gamma ray burst, or whichever you favor. So that's a big mystery. So in the meteorite, then you have the chondrules, and then in between you have what is called the matrix. And the matrix in the carbonaceous chondrites is basically just your interstellar dust compacted into something that sticks the chondrules together. So if you're an astronomer and you're interested in interstellar dust, then the matrix, it's actually not the chondrules that's interesting, it's the little black stuff in between that you want to look at. And Johann, he said, well, it was the first time that was on stardust, but that's not true because women have actually collected stardust from carbonaceous chondrites, because some of the material found here in the matrix is actually unaltered stardust or unaltered material from stars which have not been reheated or changed during the formation of the solar system. Another type of meteorite, which makes up about 7% of the falls and almost nothing in the museums, is achondrites, and they come from planets. So they are either from the moon or from Mars or from extinct asteroids. And since they come from the surface of a planet, they are very hard to distinguish from any kind of rock from the surface of the Earth. And there's a group called the ATD, which are probably from the asteroid Vesta. Then there is the SMC group, which are meteorites from Mars. Then there's a group called Urites, which probably come from the asteroid of Nysa. And then there's the Uralites, which probably comes from a C-type asteroid, but we don't know because we haven't really been close to the C-type asteroids. The stony iron meteorites come in two different flavors. There's the palladites, which are really beautiful because they have these sort of glassy-like structures in the middle, and then there's something sort of metal rock just blend together. And what we think is that if you have a planet, a minor planet of some kind, then you will have, if it's big enough, then it will undergo chemical differentiation, so that you will get an iron core, and then you will get a silicon mantle, and that's how we expect that the Earth looks like. So you get iron in here, then you get a layer of iron stone right here where you have a mix, and then you get something stone silicate out here. So it's actually believed that you have iron meteorites are pieces of a core of a distinct planet, and these iron stonies meteorites comes from the rim between the iron core and the silicate mantle of the planet, and that the achondrites are pieces of distinct planets. So this makes iron meteorites, even though they don't only make up about 6% of the falls, they're very common in the museum, they make it very interesting because it gives us an opportunity to study the core of the planet. And it's not so easy to drill a 6,000 kilometer deep core into the center of the Earth and see what the iron core of the Earth looks like. But I mean, here we have, they come by themselves to us, and we can study the cores of other planets. And iron meteorites typically look like this, and if you find this in your garden, you will think that it's weird. So it's more likely that you'll pick it up, and if you pick it up, it'll be really, really heavy, so you will know it's not an ordinary piece of rock. So how can we know that it's from the core of a planet, that it's not just a piece of iron from the surface of a planet? You know that because if you cut the iron meteorite into slices, and you etch it, then this very characteristic pattern shows up, which is called the Wittmann-Staff pattern, which is due to the fact that you have iron and nickel, which sits in two different crystal structures next to each other, and they only make this kind of crystal structure if you cool down the iron by 1 degree every 10,000 years. So you have a very, very slow cooling. And then it's very easy to calculate the other way, saying, okay, if you have a chunk of iron and you want to cool it down so fast, how thick a mantle do you need outside to sort of keep it warm for that long? And that's why we can be sure that it is from, it's not alien spaceship or something, it is actually probably a core planet. Just to sort of remind you of what the solar system looked like when it was formed and what it looks like today. So we have the inner planets, then we have the outer planets, and then we have the asteroid belt right here in between. And the interesting thing about where the asteroid belt is the snow line, as we discussed yesterday. This is actually where water starts freezing out, while in here you don't have any water. And that's why there's the whole discussion about water on Earth, because when we do models of planet formation, then all the inner planets don't have any water because water has been evaporated away because the temperature was so high. So you form a very dry planet. And you think, okay, maybe that's not a very good model to form a dry planet because it always rains. But if you think of it as an astronomer, then the Earth is very, very dry. There's no water on Earth at all because, I mean, it's 12,000 kilometers in diameter, and then you have 2 kilometers of water. So water is not really there, so it's not really a problem. But out here where the asteroid is, that's exactly where you have the snow line. And that's why, although asteroids are just sort of a piece of junk which never formed into a planet between Jupiter and Mars, it can probably tell us a whole lot about how the solar system formed, because they are at this very interesting place or what formed at this very interesting place of the solar system. So, the interesting thing about meteorites is we have about 10,000 different meteorites. They originate from probably 100 different planets. They come to us for free. I mean, just imagine if we had to fly out and do sample return missions. But the only problem is we don't exactly know where they come from, and we cannot decide which ones are coming. So the big thing in studying meteorites is how can we link them to asteroids? How can we find out which asteroids they come from? And how can we understand it? And one way, being an astronomer, is that you put light on your meteorite, and then you take a spectrum, and then you take a telescope, and then you look at the asteroids, and you make a spectrum, and then you compare them to the two, and if the spectra are alike, then the mineralogy is alike, and then you know, okay, this meteorite came from this asteroid. The only problem is that if you do that, then you get basically no match. There's basically none of the meteorites which have a spectrum that characterizes the spectrum you see of an asteroid. So that's one thing. The other thing is, how did the meteorites get from the asteroid belt to Earth? That occupied people for years, but now it seems quite straightforward. That due to the resonances that Harry was also talking about between Jupiter and the Sun, then you have certain places in the asteroid belt that once the asteroids get perturbed into these Kirkwood resonances, they are automatically sent into the inner solar system. So that problem is sort of solved, but it's not solved. Why do the meteorites' spectral characteristics look so different from the asteroid spectral characteristics? So we have about 14 different classes of asteroids, and only 2 classes have been identified with a certain group of meteorites. And here are some of the nice spectra where the points are the asteroids, and the lines are the laboratory spectra measured from the meteorites. So you can see at least we have 2 classes which seems to fit, and that's the meteorites from Vesta, which seems to be a very, very good fit, and the only one where everybody can agree that this group of meteorites is definitely pieces of Vesta. So what is the problem with asteroids? One of the problems is we've not really studied them very close. I mean, this is the close-up of the 4 asteroids we've been close to. All the other asteroids are just little dots, because every time we send out a space mission, they're always dominating when they fly through the asteroid belt, so we don't have very many pictures. The other problem is, of course, that they're quite small. They have a low albedo, so they don't send out much light. So happy we were when it turned out that the near satellites suddenly had a chance of, had some extra fuel, and they had to find out what to do with it, and then they said, okay, we'll try to land it on an asteroid. Is there anyone around? And they said, we landed on Eros, and the chance that it would work was actually 1%. So I didn't stay out that night because I was sure they were going to fail, so it would be a waste of a night's sleep. But they succeeded. I mean, they actually landed. And here's the close-up of Eros, and you can see it's just this potato thing spike. And the real surprise came during the descendants down to Eros, because, I mean, this asteroid is not smooth at all. I mean, it even looks like it's dust covered, right? And that's really weird, because you have this little body, 50 kilometers in diameter. How can it contain dust on the surface? But it sort of gives us the loophole of not understanding how to connect the meteorites with the asteroids, because the meteorites, I mean, they have been peeled off the surface on the way down, and when we measured in the lab, we measured this very clean stone with no dusty surface, and the asteroids probably have a dusty surface, and the dusty surface probably comes from space weathering. I mean, electrocharged particles, the sort of over 4.5 million years sort of alter the surface. So maybe that's the reason for why the spectra don't fit. Another thing that we have is interstellar dust particles, which comes in 2 different flavors. There are some which contain a lot of volatiles, and they are believed to be cometary dust. And then there is a whole group which do not contain volatiles, and they are believed to be of asteroidal origin. So this is basically what comes to us, and usually meteorites are called poor man's time machine, not so much because you can ride on them, but more because they come to us for free. So this is 10,000 meteorites we have with the objects out there. I mean, just the knowledge that we would gain, just if we could do that thing. But the combinations contrast is the topic of today, so why are they particularly interesting? And the reason they're interesting is because they contain the original material from the solar system. They contain the dust, which was present in the interstellar cloud. They have not been heated to above 50 degrees, and we know that because they contain water. They contain some of this carrageen, which would get different if it was heated to about 100 degrees. They contain pre-solar grains, stardust, which would have altered its mineralogy. They also contain organic material, polyaromatic hydrocarbon and amino acids, and even some sugars. And then they have something which is called calcium aluminum rich inclusions, which are probably sort of the first thing that condensed out of the very early nebula. So if one plots the abundance of one of the carbonaceous chondrites, the one where we have most material, called the Allende. That's why when you see studies on carbonaceous chondrites, it's almost always Allende, built in 1969, and we have 2,000 kilos, so it's the cheapest one if you want to do an experiment, because there's a lot of material. But if you take the abundance of that meteorite and plot it against the abundance of elements in the sun, you can see it falls on a straight line, indicating that the abundance of Allende is actually representative of the abundance of the sun. And if you plotted the Earth against the sun, it would not at all be the case, because the minerals on the Earth are not at all representative of the original minerals or the original chemical composition of the sun, simply because of the temperature gradient that the sun formed close to the sun, while Allende formed far away, that you actually had all the material present. So if you wonder about the noble gases, the nitrogen, the hydrogen, the carbon, and the oxygen, it's because it's volatile, so it's very hard to incorporate these atoms into minerals, so that's why they are deficient in Allende, while lithium is overabundant in the meteorite compared to the sun, and that has to do with the fact that lithium very easily gets destroyed in the sun. 5 minutes. Okay, I thought you had 5 minutes. So, the stardust, which was found, was identified in 1987, called pre-solar grains, which are grains which are originally stellar dust, which has preserved its characteristics, and they come in different flavors. Diamond is the most abundant, silicon carbide, graphite, and aluminum oxide, and if any of you can remember your geology, you are aware that we have sort of the hardest mineral, the third hardest, and the fifth hardest. So the reason they survive are because they're tough, so it's not necessarily the dust that stars make most of it, but it's the ones that has the best chance of surviving both the formation of the solar system and getting incorporated into the meteorite. So here's a cartoon illustrating, so you have dust forming in what is called red giant stars, that means the sun in 5 billion years. You have this dust forming in supernovae. These dust grains get thrown into the molecular clouds, out of which you form the solar system, where some of the dust grains are preserved into meteorites. Then you can extract them, you can study them in the lab, and it's a complete new situation for astronomers, because it means that we can study them with all the details of what you can do in the lab, instead of just having a telescope and having to look at spectra. So it's giving us a whole wealth of new information. So there's not a lot. I mean, don't drill the diamonds, it's not going to make you rich. It's about 1,000 parts per million, and then due to the isotopic compositions of these different grain types, we can actually also pin down where they come from. So the diamonds have an isotopic signature of supernovae, while silicon carbide, most of them come from carbon-rich giant stars. There's a small subgroup from supernovae. The graphite is from supernovae, and a very small subgroup from carbon-rich solar-type stars. You have aluminum oxide, which is from... So that's what's so sort of interesting about these grains, is that you can actually pinpoint not the particular star, because that's that by now, but which type of star that it originally came from. So how can we actually know that they are pre-solar and not just minerals that formed in the solar system? That again has to do with the isotopes. For instance, here for the silicon carbide grains, if you plot the nitrogen against the carbon isotopes, had it been solar, all the grains, all the isotopic ratios of the grains would have been found here, but as you see, they're scattered all over. And if you're wondering, thinking silicon carbide, that's silicon and carbon, so why is she plotting nitrogen? That's impurities, where you can have a nitrogen atom sitting instead of a carbon atom in the crystal structure. So you plot the impurities. And then it will be so that the solar type grains form, solar type star grains fall up here, while the supernova grains, they fall down here. So, but carbonaceous chondrites, they spell life, and since the first claim of biological life in the 1960 of Barton-Nagy in the organic carbonaceous chondrites, which fell in 1864, then there's been a continuously ongoing debate. And another thing that's been an ongoing debate is the discovery of amino acids found, whether it's a racemic mix you have in the meteorite or whether you have an overabundance of the left-handed form. And then a few years ago, some sugar-like objects were found in the Murchison carbonaceous chondrites, and here is Cooper, and of course he was pictured with a sugar ball in his hand when he discovered this. So pre-slime material seems to appear in these carbonaceous chondrites, but there is a catch-22 when it comes to looking for life in carbonaceous chondrite, and that is, if what you find looks earthly, then it's probably deemed to be contaminated. If what you find looks non-earthly, then it's probably not biological and therefore not interesting. So it's really, I mean, it's uphill. So here's some pictures from a paper in '99 of a Russian group who claimed that they actually found some fossils, and they base it only on morphology. And morphology is very dangerous because you can have non-organic things going on, which can give you a morphology which looks very organic, so one should always be careful only looking at morphology. So I would say the problems with the carbonaceous chondrites is that they have always been around for a while before we found them. Except for Allende, where we saw it fell, and it fell in '69, and it was very fortunate it was in '69, because '69 was the time of the lunar missions, which meant that we had all these very nice clean labs just hanging around waiting for the lunar rocks to come back. So it was actually picked up and then it was sent to the lab, and the same thing with the Murchison meteorite, which also fell in '69, which is sort of a coincidence. You basically have 3 carbonaceous chondrites, and 2 of them chose to fall in '69 when the clean labs were already. And they have been handled carefully, and they have found amino acids, and they still find amino acids, but there's always this thing about contamination. I mean, okay, we've been around here for 140 years. '69 is long ago, the youngest of you here were not even born then. So there's always, how can you exclude contamination? And then it's become a particularly bad case when Tacky's Lake, there was a meteorite falling up in northern Canada called Tacky's Lake in 2001. And it was seaborne, so they went out for it right away, and it fell, and it was during the winter, which was very fortunate. So, and it sort of froze in at once, and it was picked up, and it was kept frozen, and it was picked up in a clean way, and it was studied in the lab, and they examined it for amino acids, and they found nothing. And that sort of either tells you that Tacky's Lake was formed somewhere else in the solar system than the other one. It was an oddball, but it could also tell you that maybe amino acids are not part of carbonaceous chondrites, and maybe what we see in the other ones are just contaminated. So I'm actually pessimistic. I think it's not very likely that they will give us any clue to the building block of life, because you can never rule out the contamination thing unless we have a new one falling and we know exactly what we're doing. However, they can tell us a lot about what happened in the early stages of the solar system, so I'm sure that carbonaceous chondrites are the key to understanding planet formation, but I'm not so sure if they're the key to understanding the origin of life. I mean, they might help, but they're not key Rosetta Stones. What we really need is a sample return to the asteroid belt, and preferably the outer asteroid belt close to Jupiter, so we can see if the outer asteroids are primitive and look like carbonaceous chondrites.
Thank you. Questions?
We did not talk about the micrometeorites which are collected in Antarctica, and I mean they find also a lot of organics in them. Okay, there's also the contamination question.
Yeah, I mean the contamination only gets worse as the meteorite gets smaller, right?
Yeah.
Because then you have larger surface to volume, and it's easier to penetrate. And I mean, just with the Martian meteorites, which was found on Antarctica, where they found this Microsoft, maybe microfossil in 1996. And there's still the debate going on, and now the latest thing is that they examined all the Martian meteorites, and it seems like maybe it was contaminated, maybe things get more contaminated also in Antarctica than they thought. Because they then started examining the Antarctica meteorites to see how fast terrestrial life could actually penetrate into a meteorite, and it was scary fast, right? And the problem with the things they collect at Antarctica, they have been around typically for some 1,000 years before they picked up. So you can never rule out the contaminants. I mean, it might not be a big problem, but the problem with extraterrestrial life is it needs extraordinary proof. And I think that's very hard to get from the meteorites unless you sort of catch them when they fall.
One question regarding this source of amino acids point now that they are mostly the same. Doesn't that indicate that they are not Earth originated?
Or it just indicates that they have, I mean, if you can have an overabundance of left-handed, but then the whole thing comes to a symmetry with time, right?
Yeah,
if it was biological originally.
Yeah, and there's a lot of amino acids are not found in the biosphere.
Yeah,
So those should come
yeah.
from Earth.
There are 8 amino acids found in merchant cells which are not present on Earth. So they're basically the ones that people are focusing on to see if there isn't. And this little Italian woman that you asked, I mean, piece
It's from US, but she is Italian.
Yeah, I mean, she has been done some very thorough investigations and done very nice work on it. And she claims that of these 8 non-terrestrial amino acids, you do have a non-racemic, you have an overabundance of the left-handed side, which points at that maybe this thing about the left-handed is something interstellar or maybe even Big Bang, who knows, but something which did not occur on Earth but actually occurred.
And this sounds very intriguing, this, that if these amino acids are non-Earth origin, then they would also be pre-solar. As the rest of the
Yeah.
So amino acids and organics are
Yeah.
the stardust.
Yeah, I think, I mean, it's, it must be, I don't know if you can form amino acids during the solar system. So I think it's, I mean, amino acids have been seen in space, so it's most likely just, the amino acids present in the interstellar cloud form. I don't think conditions in the solar system nebula is very good for actually forming amino acids. It's more good for destroying them. So I think what you find is, if it's not terrestrial, then it's interstellar.
But I mean, we had a discussion in the interstellar medium. I think the only amino acid that's found, and she says it's confirmed, is lysine, the most primitive one. So that's a problem that we don't find the amino acid in the interstellar medium. But maybe it's a development actually.
Yeah, I would say it's probably more, an astronomy telescope problem than it's necessarily a problem of them not being there. I mean, as an astronomer, if you find one, you expect they're all there, right?
Yeah, look at this one.
Okay. Any further question? But there's another intriguing thing with the Parkinson. That says that these amino acids cannot enter in any relation with things on Earth.
No. But at least it's not contaminated, right?
Right.
But you would say it's not extraterrestrial because it's not biological, because you don't recognize it as being. I mean,
No. My point was actually the following: as we don't find them on Earth, then it could sort of, if they had any viability at all, it would indicate that nothing like Murchison has ever happened before. But if they just disappear by then we cannot rule out. Any further? Then that concludes the session. Thank you.